Time to start class, and I've got recording and audio. So, I see you all survived the great tornado outbreak. None of you got flooded out. Thank you. Does anyone else have any homework to turn in? Does anyone else have any questions from their homework? Morning. Say again? No. I'm not going to go back and rederive these equations, but I do want you to make sure you have them written down because you're going to need them over and over and over again. So, no one has any questions from the homework yet? All right, well then let's start by working through some of these problems and these examples they give us in the book, because that's what I was just saying before class started. This is how you learn the material, by using it and doing it over and over again. As one of my undergraduate instructors told me in an undergraduate algebra class, said, sometimes all you can do is just do it till you believe it. So, say again? Yeah. Yep. You can work through and do the math, and you can prove that whole limit as delta x approaches 0 or delta t approaches 0. You can work through the math and the algebra and prove it, but yeah, at some point you just got to do it till you remember it. And I think I told you that's what kicked me so hard in integral calculus, was that you've all got to witness my steel trap memory firsthand. So the memorizing all those integral tables just that kicked me hard. But I got through it, and so can you. Now, who can tell me the special condition that must be true in order for these equations to be valid? Acceleration has to be constant. What if acceleration is 0? Then, as long as it stays 0, acceleration is still constant. If acceleration is not 0, as long as it stays constant, these equations are valid. So if you'll turn to page 29, let's look at example 2.7. Runway design. You are designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second, which is 100 kilometers per hour. and can accelerate at 2.00 meters per second squared. A, if the runway is 150 meters, can this airplane use the airport? Can it reach the required speed of 28.7 meters per second in 150 meters if it's accelerating at 2.00 meters per second squared? Which of the four equations would we use? That's right. Why? Because we don't have a time. What we have is a distance. We have x minus x sub naught, which is 150 meters. We have a total displacement. And we know we have a minimum velocity that we have to reach, and we have a constant acceleration. So we have all of the information we need to solve for velocity squared, for the velocity that we'll achieve in that distance. So let's write that out. V squared, the maximum speed it can reach in 150 meters, is going to be V sub naught squared plus 2 times A times x minus x sub naught. What's the V naught squared? What's V sub naught? It's going to be 0. It starts from rest. So that goes away. And we know A is 2.00. So we've got 2 times 2.00 meters per second squared. What's x minus x sub naught? 150 meters. So that equals, what's 4 times 150 meters? 600? So that's going to be 600 with 3 significant digits, meters squared per second squared. Does everyone see where I got my units? Meters per second squared times meters gives us meters squared per second squared. And that's supposed to be equal to our velocity squared. And if we take the square root of both sides, meters squared per second squared, taking the square root, becomes meters per second, which is velocity. So, everybody break out your calculators. Y'all got some arithmeticking to do. To 3 significant digits, what is up? How many significant digits do we have? Did they say that the runway was 150 or 150.0? Nope, just 150 meters. How many significant digits are there? So, to 2 significant digits, what is the square root of 600? You got an answer? Say again? 24.49? I don't have my calculator with me in here. You got 24.49 meters? So that would be How much? To two significant digits? No. You could round it to this to 5 and then that to 5. But I would go with 24. Because that third did that 4 right there. This is one that you could do it either way and be justified to do it. Or you could just make it out to 3 and call it 24.5. In any case, can this airplane use this runway? No, it has to reach a minimum 28.7. meters per second. And so it cannot use this 150 meter runway. So now let's use this same equation, but this time let's find out how long do we need the runway? Yes, I know. How long runway need? Question mark. Learn to speak English I must, before teach I do. All right, so what is the minimum distance this runway can be? Well, if we require a final speed of 28.7 meters per second, square that, and we're still starting off at 0. What is 28.7 squared? $823.69, and we're going to hold on to all those extra decimal places until we get to the end. Meters squared per second squared is equal to 2 times 2.00 meters per second squared times x meters. Okay, what is 823.69 divided by 4? Yeah, hold on a minute. Nope, we're good. Say again now. 823.69 divided by 4 is? $205.9 meters squared divided by meters per second squared divided by meters. Can't write or talk this morning. Meters squared per second squared divided by meters per second squared leaves just meters. And that's equal to our minimum length. So, in order for this plane to use the runway must be a minimum of 206 meters long. Has anybody else come in since the sign-in sheet went around? Yeah, Tony, here, pass this back, please. Get her and him too. Everybody see how that one was done? this is this equation, your minimum velocity that you need to achieve squared. So it is 28.7 meters per second is the minimum speed it has to achieve. And because I'm using that equation, I start with that velocity squared. And that will be equal to the rest of this. How did I get rid of delta? I just didn't write it. It's the same thing. X, delta x, it's the distance, the displacement. Technically, you're right. X is a position, not a displacement, but I got lazy. Shy or Tony, do either of y'all have any questions from the homework assignments? No? All right. If you'll turn over to the next page on page 30, they go through a set of steps for you to look at when you're solving these problems. And I want to go through each of these steps with you because they really will save you. They may seem kind of trivial and, tedious, but the fact is, if you think about these things as you work through these problems, you'd be surprised how often they'll save you. Starting with this one. 1, read and reread the whole problem carefully before trying to solve it. Why is that important? I can't tell you how many times I've graded your homework and found where you got to a final answer, and I was like, that's very true, but that's not what they asked for. They were asking for how long is the runway, not what speed is it going to get to. Yeah. Read the problem. Make sure you're answering the question that's asked. You're solving for what the problem asks you to solve for. Decide what object or objects you're going to study and for what time interval. And as I pointed out yesterday, you can usually choose T0 as being time 0 or 0 seconds. 3, draw a diagram or picture. I cannot stress enough how often doing that one simple thing will just clarify what you're doing for you. It'll make it more obvious, more plain what you're doing. Write down what quantities are known or given. Always, always, always. Write them down and label the drawing when you do a drawing. And this will always be true, whether we're doing kinematics or energy or work or whatever, simple machines. Then think about what principles of physics apply in that problem. Now, next, consider which equations or definitions relate the quantities that are involved. And before using them, be sure their range of validity includes your problem. For example, the equations like we've got over there are only valid under what conditions? Tony or Shy? Either one of you? If what's constant? Acceleration is constant. Exactly. Who has the sign-in sheet? Oh, I do. Well, that was sneaky. Here you go, Megan. We just did this a moment ago when we set up this problem to solve. First question I asked, which equation should we use? That's always an important step. Look at what your information you are given, what you know, what quantities you are known, and look at what quantity you want to solve for. Pick your equation accordingly. Would this equation have been a valid equation to use in the problem we just worked on, the designing a runway length? No. Now, if we wanted to know how fast must the plane accelerate in order to use that runway, then we still would have used this. But if we wanted to know how long is it going to take the plane to take off, because now we're worried about air traffic. How many planes do you need to get in and out in a certain amount of time? Then we would be solving for time. Seven, and this is one I've already pointed out to you before. I'm going to repeat it again now. Carry out the calculation keeping as many digits as your calculator will hold. If you have to start over and do repeat calculations, keep 2 or 3 or 4 extra decimal places that are beyond the significant digits. Why? Why do you wait till the very end to round off to the appropriate number of significant digits? Because rounding off will affect your answer. Every time you round off a calculation, you're introducing a little bit of rounding error. So you carry out all of the calculations with as many significant digits and with as many decimal places as you can carry through. Round down to the meaningful number of significant digits only after you've got your final answer. Number 8. And let's see a show of hands. How many of you is this starting to sound like redundancy, like I keep saying the same things over and over again? Think about your answer. Is it a reasonable answer? If we were solving for this, for this length of runway, and we found out that the runway had to be a minimum of 27 millimeters, would that even make sense? No. So, whatever answer you come up with, think about, does it make sense that this would be the right answer? Plug it back into your original equation that you started with and confirm that it actually is a solution to that equation. You'll find out a lot of times that you will catch mistakes that you've made. And finally, in this long and tedious list of redundancy, check your units. We did this was an exercise we did a couple weeks ago in dimensional analysis, looking at the potential equations, or different equations that were each potential solutions. And all you had to do was under dimensional analysis to realize, wait a minute, this equation just doesn't work. Check your units. If you're solving for how long it takes the airplane to get from one end of the runway to the other and your answer comes out in meters per second, that doesn't make sense. You're looking for seconds. If you are looking for a velocity and all you end up with are seconds, it doesn't make sense. You go back and figure out where you messed up. Let's work another example. Acceleration of a car. And those of you who only came in late, get out your calculators. I don't have mine today, and it's not like I'm fond of using it when I have it. Acceleration of a car. How long does it take a car to cross a 30.0 meter wide intersection? After the light turns green, if the car accelerates from rest, at a constant 2.00 meters per second squared. There are our known quantities. What is the question asking? What are we trying to solve for? How long does it take the car to cross the intersection? After the light turns green. You've all heard about the shortest span of time that's possible to measure. The shortest measurable time period is the time between the light turning green and the sound of the horn from the car behind you reaching you. Given this question, first of all, what are we going to expect for our answer to be? Seconds. We're looking for time and units of seconds. Which of these equations should we use? The top one? Yeah, we don't really have any velocities, and we're looking for time. There you go. Okay, x is equal to x sub naught plus v sub naught t plus 1/2 a t squared. Are there any of those that we do not know? We can define the starting point as x equals 0, which means this becomes 30 meters. We know v sub naught is defined as 0, and we know that this is defined as 2.0 meters per second squared. So now let's rewrite this equation with the values that we know. 30.0 meters is equal to 1/2 2.00 meters per second squared times t squared. Well, fortunately, we don't have to break out the quadratic equation for this one. That will not always be the case. If you're not familiar with how to use the quadratic equation, you need to get familiar with it, because you never know when you'll be on a test And you'll need the quadratic equation, and some thoughtless professor may not have remembered to erase it off a board, but you can't always rely on that. So, and in case that went over some of your head, I'm pointing at the quadratic equation over there on that board that hasn't been erased for 2 semesters at least. So, knowing the equation doesn't mean you know how to use it. This time it doesn't really matter. How do we solve this for t? Say again? Divide 30 by 1? I'm sorry. No. Okay, one step at a. I think you sounds like you got the right idea, but you're maybe not taking it one step at a time enough. First, we multiply both sides by 2. And then we divide both sides by 2. If the acceleration had not been 2, that would no longer be the case. So we divide both sides by 2 and we get back to 30 meters is equal to t squared. I'm sorry. Not 30 meters. What do we get when we divide by 60 meters by 2.0 meters per second squared? (30 seconds squared is equal to t squared. Remember, you always want to check your units at every step. Make sure you're not messing up. Now, when we take the square root of 30, the seconds squared becomes seconds. So, what's the square root of 30? Say again? 5.47 to 3 significant digits. Does everybody else get the same answer? Anybody have any questions about how we get this? The book got a different answer. Book says 5.48. 5.477, then that would be 48. Next problem in the book is one on braking distances. Okay, the only real trick here is that they're pointing out that acceleration in this case is negative. It's braking is acceleration. And since it's our lab this week, I do want to talk about free-falling objects. This is what we're going to be doing in lab tomorrow. Is we're going to be experimentally confirming that these equations do accurately calculate the motion of an object as it moves under constant acceleration. Gravity is a constant acceleration. So these equations should be valid, right? What we're going to have to change when we talk about free-falling objects is the direction of the axis. We're still talking about one-dimensional motion. So instead of x, we're going to talk about y, where y sub naught will either be where you start and you calculate some negative y, or you define y sub naught as the ground, and then you solve for some y at which you began. So instead of x and delta x, we'll be dealing with y and delta y. And a in free fall is what? Minus 9.8 meters per second squared, which is g, the acceleration due to gravity. And I want to point out to you, you can observe this as we work through these problems. I could just as easily define the acceleration as a positive number if I define the positive y-axis as pointing down, pointing towards the center of the Earth. Of course, that would be backwards to the way we've all thought about it our whole lives. So let's do this as an experiment here. Got a piece of paper right here. And, this will work. I have two objects. If I drop both of them at the same time, which one will hit the ground first? Why? The paper won't? The paper won't hit the ground first or at the same time? Why not? Because in this shape, the air resistance is not negligible. It takes quite a bit longer for the paper to reach the ground. But only because we couldn't neglect wind resistance. If we can neglect air resistance or drag, the same piece of paper falls at exactly the same rate. Now, the book goes through a whole lot of other examples. They talk about putting a stone and a feather in a vacuum tube, and then the stone and the feather will both fall at the same rate. What I want to do is work through one or two of these problems using these kinematic equations for a free-falling object. So this all started with Galileo dropping things off of a tower. So let's do example 210, falling from a tower. Suppose that a ball is dropped from beginning at rest. So we have right off the bat, we know V sub naught is 0. We're dropping a ball, that means we're starting from rest. How far will it have fallen after a time t1 equals 1.00 seconds? Okay, 3 different times. T1 will be, where'd it go? There, 1.00. T2, 2.00 seconds, and T3, 3.00 seconds. And it says ignore air resistance. Okay. So let's draw us a picture. We're going to define this as minus y, and here we'll call y naught as 0, where we're starting from. And what we're looking for are what? We're looking for how far the ball will fall. So we're looking for distances, meters. Now, which of these equations will we use? The one with the arrow, yeah, the x. Only we're going to use it in this form. Y equals y sub naught plus v sub naught t plus 1/2 a t squared. But what's a? Minus 9.8. So it's actually going to be y sub naught plus v sub naught t minus 9.8 meters per second squared over 2 times t squared. Well, what's 9.8 divided by 2? Say again, 4.9? So our equation is going to be y sub naught plus v sub naught t minus 4.9 meters per second squared times t squared. We defined the starting y sub naught as 0, and v sub naught is also defined as 0. So our equation becomes y equals minus 4.9 meters per second squared times t squared. And once again, we are spared the dreaded quadratic equation. If we simply plug in 1.00 seconds, what is 1 squared? 1. Y then becomes minus 4.9 meters per second squared times 1 squared second squared. The second squared cancels the per second squared, and we're left with y equals minus 4.9 meters. There you go. What about when t equals 2.00? This becomes 4 seconds squared. So y equals minus 4.90 meters per second squared times 2 squared is 4.00 seconds squared. Second squared cancels those. 4 times minus 4.9 is 19 point something? 19.6. And now for t equals 3 minus 4.90 meters per second squared times 3 squared is 9, right? Am I right? Okay. 9.00 seconds squared. They cancel, and 9 times minus 4.9 equals 44.1. Because I defined y going down as negative. Now, if I had defined this as 0, if I had defined the ground as y equals 0, then y naught would have been some positive number, and as long as it was greater than 44.1, then we would have solved it with, but instead of starting off with just minus 4.9, we would have been starting with y equals, say I said defined the top as 50 meters, then we would have been starting off at 50 meters minus 1/2 g t squared. And so we would have been subtracting 4.9 meters from 50 meters. You see how that would have made the difference? Then we would have subtracted 19.6 meters from 50 meters. And finally, we would have subtracted 44.1 meters from 50 meters. And we would have been ending up at positive y values till we fell for long enough for it to get all the way to 50 meters, at which point it would have hit. Any other questions? All right. We got one row. Let's do one more here just before we leave for the day. We're going to do a ball thrown upwards. So, person throws a ball upward into the air with an initial velocity of 15.0 meters per second. That's a positive 15 meters per second. I'm sorry, 15.0 meters per second. 3 significant digits. How high does that ball go? So, let's start by drawing our picture. 15 meters per second. The ball is going to travel upwards and then come right back down. And we want to know, how high will it go? Y equals some number of meters. So we're going to define this as 0 meters. Okay, we're going to define our starting point as the ground as 0. Now, which of these equations does it look like we're going to want to use? Say again? This one right here? That would be my choice. Why is that your choice? Exactly. We're looking for a distance, total displacement. Now, this would be y and y sub naught, but it's the same equation. We just took the x-axis and we turned it vertically, 90 degrees. So, they're looking for v squared equals v sub naught plus 2a y minus y sub naught, except 2a plus 2a is actually minus 4.9, minus 9.8 divided by 2. And this time v sub naught is not 0. What is it? 15.0 meters per second. Say again? Because it's minus 9.8 meters per second squared, because gravity is always accelerating down in the negative direction. And it's divided by 2. It's 1/2 that. Oh, thank you. You're right. Excellent catch. So it's going to be, I'm working with the wrong equation there. Minus 2 times 9.8 meters per second squared times y minus y naught. And what's 2 times 9.8? 19.6? Is that right? So v squared equals 15.0 meters per second minus 19.6 meters per second squared times y minus y sub naught, where y sub naught is 0. We defined that as 0. So, now here's where you have to do a little bit of thinking. Right now we have, what do we have here? We have v squared equals 15.0 meters per second minus 19.6 meters per second squared times y meters. We have 2 unknowns and 1 equation. That's a problem. You can't solve for 2 unknowns with only 1 equation. You can solve 2 unknowns if you have 2 independent equations. We only have 1 independent equation. So, put your thinking cap on. How do we solve this? What is the next thing we have to think about to figure out before we can just do the arithmetic? What is our question that we're asking? How high is it going to go? So, what will the velocity be when it gets right there at the very top? The velocity is going to slow down. It starts off at 15 meters per second positive, and it's going to slow down because it's being accelerated in the opposite direction. It's like applying the brakes. And it's going to continue to slow down until it stops. At that instant, its velocity will be 0 before its velocity goes negative and it starts falling. So, that velocity squared is simply 0 squared. And 0 squared is still 0. Now, how do we solve this? Subtract 15 from both sides and we end up with minus 15.0 meters per second is equal to minus 19.6 meters per second squared times y. And we divide both sides by minus 19.6 meters per second squared, and we get minus 15.0 meters per second divided by minus 19.6 meters per second squared. When we divide meters by meters, they cancel. Seconds divided by seconds squared by negative seconds squared. What does this come out to? One over seconds divided by 1 over seconds squared. Division is multiplication by a reciprocal. So that is equal to 1 over s times s squared over 1. We're left with units of seconds. Now, a negative divided by a negative is a positive. So what's 15.0 divided by 19.6? Say, I couldn't hear you. Say again? No. That ball only goes up 0.77 meters? Really? B sub naught was squared. No, it was 0 squared. 0 times 0 is still 0. Does that make any kind of sense? There you go. No. We got to find out. We got to go back and figure out what we did wrong. And we're out of time to do it. I'm going to let y'all puzzle on that one. See if y'all can see who can figure out what went wrong here sometime between now and lab tomorrow. No. The bonus will be actually learning something. Anybody did not sign the sign-in sheet?